Welcome back to Deep Tech. This is episode 2. Last episode, we mapped where classical reservoir simulation hits its wall. Today we go upstream, all the way to the molecules. Because if we can't simulate the chemistry, the climate math doesn't close. This is quantum chemistry for catalysis. The molecules that decarbonize the planet, and the qubits that are about to design them. In episode 1, we built the case that classical simulators are running out of room. Petascale machines still can't capture reactive transport, multi-component flow, or the geological uncertainty that real CCUS and hydrogen storage projects throw at them. We ended on this line. The hardest physics is chemistry, because every trapping mechanism, every recovery curve, every microbial loss, they all collapse back to reaction rates. So today we change the layer. We zoom out of the reservoir and we zoom into the active site. And we ask one question. Can quantum computers solve the molecule problem that's blocking decarbonization? 3 industries, 3 numbers, 1 missing molecule each. CO2 capture today costs around $120 per ton. To scale to gigatons, that has to drop by a factor of 5. The bottleneck is amine kinetics and sorbent design, chemistry. Modern electrolyzers cap out around 60% efficiency. The plateau is the oxygen evolution over potential, and iridium oxide, the gold standard catalyst, is one of the rarest stable elements on Earth. Globally, ammonia synthesis consumes nearly 2% of all energy on the planet, at 450 degrees Celsius and 200 bars of pressure. Meanwhile, soil bacteria do the same reaction at room temperature in a puddle. Each of these gaps is gated by a catalyst we don't have yet. And finding it isn't a problem of motivation. It's a problem of simulation accuracy. Here's how we'll do it. 6 chapters. First, why catalysts decide whether decarbonization actually happens. Then the quantum chemistry stack. Then the algorithms, VQE, QP, embedding. Then the 2 flagship targets, CO2 reduction and green hydrogen. And we close with the industry roadmap. Who's building today and what 2030 actually looks like. Let's start with chapter 1. A catalyst lowers the mountain. That's the whole job. A reaction proceeds when molecules climb an energy barrier, the transition state. A catalyst opens a new pathway with a lower barrier, so more molecules make it across in less time. The reactants and products don't change. Only the climb between them shrinks. Notice what a catalyst does not do. It doesn't change thermodynamics. Equilibrium stays where it was. It isn't consumed. It just keeps showing up at the active site, lowering delta G double dagger, again and again, billions of times per second. The whole game is engineering that exact energy. 3 reactions. Each one is worth a Nobel Prize. 1 already won, 2 still wide open. CO2 reduction. Turn waste molecules into feedstock, fuels, plastics, materials. It's a multi-electron transfer, at least 6 intermediates deep, and the prize is selectivity over hydrogen. Water splitting. 2 molecules of water into hydrogen and oxygen. Easy to write down, brutal in practice, because the oxygen side, the OER, needs an enormous overpotential to drive. Nitrogen fixation. Haber and Bosch already won the 1918 Nobel, but they did it with brute force. Nature does the same chemistry with the FeMoco enzyme. 64 strongly correlated electrons at room temperature. We can't simulate FeMoco. That's the open prize. Quantum chemistry has a pyramid. At the bottom, Hartree-Fock. Fast, but it ignores electron correlation by construction. Above that, DFT, the workhorse of every catalyst paper for the last 30 years. It scales as n cubed, so it handles thousands of atoms. Higher up, the multi-reference methods MP2 and CASC for when DFT can't capture the physics. Higher still, CCSD, T, the gold standard, scaling as n to the 7th. Caps out around 50 atoms. And right at the top, full CI. The exact answer. N factorial. Only ever solved for tiny molecules. Here's the trade-off. DFT is everywhere, but for transition metals, errors of 10 to 20 kilocalories per mole are routine. That's enough to flip a selectivity prediction. And CCSD, T, is unreachable for any real catalytic surface. We're stuck in the middle of the pyramid with no good option. Here's where DFT silently breaks. For reasons. 1. Transition metals have many partially filled d orbitals at almost the same energy. A single determinant wave function can't mix them. The physics is multi-reference. The math says it isn't. 2. Functional dependence. PBE B3 LYP M06 omega B97XD. Every modern functional gives a different ground state for the same iron-oxygen complex. There's no first principles way to choose. 3. Self-interaction error. Approximate functionals let an electron interact with itself. The error blows up exactly where catalysis lives. Stretched bonds, charge transfer, radicals. And 4. FeMoCo, the cautionary tale. The nitrogenase cofactor. 7 irons, 1 molybdenum, 50+ strongly correlated electrons. Every DFT paper claims a different ground spin state. It's the molecule everyone wants to simulate, and nobody can. This is the wall. Quantum computers are the way through it. Chapter 2. Enter quantum chemistry, where electrons finally get the qubits they always deserved. This is the problem we want to solve. The electronic Schrödinger equation. H hat psi equals E psi. We want the ground state energy of the electrons in a molecule. Decompose the Hamiltonian. 3 pieces. Kinetic energy of the electrons. Attraction to the nuclei. And repulsion between electron pairs. The first 2 are easy. They're one-body terms, they decouple. The third, electron-electron repulsion, is the hard part. Every electron talks to every other electron simultaneously. That coupling is what blows up classical algorithms. And it's exactly what quantum computers handle natively. To put chemistry on a quantum computer, we change languages. Forget wave functions for a moment. Think occupation. Each spin orbital is a slot. An electron either occupies it, a 1, or it doesn't, a 0. 2 operators, a dagger, and move electrons between slots, and they automatically respect Fermion antisymmetry. The Hamiltonian becomes a sum over one-body terms, single electron hops, and 2-body terms, pair interactions. That's it. That's the entire molecular Hamiltonian in second quantization. And, crucially, it's almost a quantum circuit already. 3 ways to map fermions onto qubits. Jordan Wigner, the classic. N orbitals become n qubits, 1 for 1. Simple, intuitive, but the Pauli strings grow linearly with the molecule. Long circuits. Bravii-Kitaev, clever. Same number of qubits, but Pauli weight only logarithmic in n. Shorter circuits, more bookkeeping. Parity encoding. Exploit Z2 symmetries to drop 2 qubits per molecule. Free savings, manual work. In practice, modern stacks use Bravii-Kitaev with symmetry tapering. That gets you the smallest, shallowest circuits, the only kind that runs on hardware we actually have. H2, 4 orbitals, 16 dimensions. Trivial. Water, 14 orbitals, 16,000. Easy. N2, 20 orbitals, a million. CCSD, T, still handles it. An iron complex, 50 orbitals, 10 to the 15. We've left CCSD, T behind. Only DFT is left, and DFT is wrong. FeMoCo, 152 orbitals, 10 to the 45. There aren't enough atoms in the universe to store that wave function classically. Pause, but on a quantum computer, 152 qubits. Already built. The exponential wall is exactly what quantum computers were designed to climb. Chapter 3. The algorithms. 3 letters each, VQE, QPE, plus the trick that makes them industrial, embedding. Here's the loop. On the QPU, we prepare a trial wave function parameterized by theta. We measure the expected energy. We send that number to a classical optimizer, Atom, Cobila, SBSA. The optimizer picks a new theta. The QPU runs again. Repeat until the energy converges. The variational principle guarantees that the energy we measure is always greater than or equal to the true ground state. We can never undershoot. Why VQE works on today's hardware? The circuits are short, tens or hundreds of gates, not millions. The variational principle absorbs some noise, and it runs on every flavor of qubit: superconducting, trapped ion, neutral atom. This is the algorithm doing real chemistry on real hardware right now. The art of VQE is choosing the trial wave function, the ansatz. 3 families dominate: UCCSD, unitary coupled cluster, singles and doubles. Chemistry inspired. It builds the wave function from physical excitations and converges to the exact answer with enough parameters. Downside: the circuits are deep, hard for NSQ devices. QP, quantum phase estimation, the expensive cousin of VQE. The idea: encode the energy as a phase. Time evolved the system under H, and the wave function picks up a phase proportional to its energy. Read the phase off with ancilla qubits and an inverse quantum Fourier transform. 1 circuit, 1 answer, no optimization loop. The accuracy is chemical, 1 kilocalorie per mole or better. That's textbook accuracy. So why don't we just run QPE on everything? 2 reasons. The circuits are millions of gates deep, far beyond NISQ, and it needs fault tolerance. Error-corrected qubits we don't yet have at scale. For molecules the size of FeMoCo, the resource estimates push QPE past 2030. But for water, for LIH, for small clusters, QPE is starting to land. The fault-tolerant era is when this becomes the default. Let's get concrete. What does each molecule actually cost? H2, for logical qubits, 1,000 T-gates. VQE handles it today. QPE handles it today. LIH, 12 qubits, both still viable. Water, 14 qubits. By 2027, we'll have QPE on it. N2, 20 qubits. VQE is borderline already. QPE arrives around 2028. A copper CO2 active site, 50 qubits. We need embedding tricks to make it work. In FeMoCo, about 150 logical qubits, 10 to the 10th T gates. Post-2032 for a serious answer. Chapter 4. CO2 reduction. Take a waste molecule and turn it into fuel if we can find the catalyst. Different metals, different products. Gold and silver. They reduce CO2 to carbon monoxide. 2. Electron transfer. Fast, selective, but CO is the cheapest possible product. Tin and bismuth, formic acid. 2. Electron, reasonable selectivity. A hydrogen carrier candidate. Copper. And here it gets interesting. Copper is the only metal that pushes the reaction past 2 electrons. Up to 12, in fact, making methane, ethylene, ethanol. Real fuels. But the selectivity problem is wide open. And then molybdenum, iron, the earth-abundant alternatives. Almost no good data. That's quantum simulation territory. The selectivity gap between 2 products is about 0.1 electron volts. That's exactly where DFT errors live. Sabatier's principle. Activity peaks when the catalyst binds its key intermediate for CO2 reduction, the starred CO, just right. Bind it too weakly, nothing reacts. Bind it too strongly, the surface poisons. Gold sits on the weak side. Platinum sits on the strong side. Copper sits at the peak. Beautiful story, except binding energies are differences of total energies. DFT can be wrong by 0.3 electron volts on each side independently, and the difference becomes a coin flip. So we can't trust the volcano. Quantum chemistry at QPE class accuracy resolves the peak. That's how we find the next copper, or how we improve copper itself. This isn't theoretical anymore. For results from the last 2 years. 2023, Google, BASF, Caltech. VQE plus active space embedding on a copper 100 surface. Binding energies within 5 millielectron volts of CCSD, T. 2024, IBM and Riken. Sampling base quantum computing on an iron N4 single atom catalyst. Spin state ordering corrected versus DFT. 2024, PsiQuantum and Microsoft. Resource estimate for a cytochrome P450 like iron center. 4 million T gates to chemical accuracy. 2025, Quantinuum and BMW. Adapt VQE on 56 qubits with error mitigation. A working catalyst screening pipeline. Industrial pipelines are weeks behind the academic literature. The race is on. Chapter 5. Green hydrogen. Splitting water without a precious metal tax. Water splitting is two half reactions. Hydrogen evolution. 2 protons, 2 electrons, 1 molecule of hydrogen. Easy. Platinum doesn't near zero over potential. The research goal here is replacement. Get to nickel molybdenum, MOS2, single atom cobalt, anything cheaper than platinum. Oxygen evolution. 2 waters become oxygen, for protons, for electrons. For electron transfer. Hard. Iridium oxide still needs about 300 millivolts of overpotential. Iridium is one of the rarest elements on Earth. The research target, Earth-abundant nickel iron oxyhydroxide, cobalt oxide. Quantum studies are very active here. OER is the bottleneck of the entire green hydrogen economy. Whichever country cracks it first wins the next industrial revolution. Why Earth-abundant? Iridium trades around $5,000 an ounce. Global production is about 9 tons a year. Total. Even if we used every gram for electrolyzers, we couldn't build the terawatt-scale hydrogen infrastructure the planet needs. So we have to find replacements. For candidates, lead the field. Nickel iron oxyhydroxide, layered double hydroxide, one of the best Earth-abundant OER catalysts known. Co3O4, the spinel oxide, active sites and spin states heavily debated by DFT. MOS2 for her. The active sites are at the edges and defects. Quantum studies are clarifying which defects matter. And the iron N4 carbon, a single atom site, the perfect testbed for quantum embedding. These 4 molecules are where quantum chemistry meets gigawatts. Chapter 6. From lab to plant. Who's already building, and what the next 10 years actually look like. 6 partnerships shipping in 2025. Google Quantum AI with BASF and Caltech, Pharma, and Catalysis. IBM Quantum with Mitsubishi Chemical, Photovoltaics, and OLED. Microsoft Azure Quantum with Johnson Matthey and PNNL, Auto Catalysts and Fuels. Quantinuum with Honeywell, BMW, and JSR, Battery Materials and Catalysts. PsiQuantum with Mercedes-Benz, Battery Cathodes. Chuera and Pascal with BMW and Saudi Aramco, Materials and Energy. Notice the pattern. It's not just quantum companies. It's chemicals, autos, energy majors, every industry that lives or dies by the next catalyst. This is no longer R&D. It's procurement. Here's how this actually ships. A 3-layer architecture. The environment, bulk solvent, the surface scaffold, handled by force fields. Millions of atoms. Cheap. The middle layer. A DFT cluster around the active site. Hundreds of atoms. Standard hardware. The quantum core. The strongly correlated active orbitals. Tens of orbitals. Run on the QPU with VQE or QP. The technique that glues them together is called DMET, density matrix embedding theory. You couple a small impurity solver, the quantum part, to a low-level bath, DFT. The quantum cost stays bounded even as the molecule grows. This is the workflow industrial pipelines are converging on. Not pure quantum, not pure classical. Hybrid by design. Quantum where it earns its keep. Here's the timeline. 2025, this year. Embedding demonstrations. VQE plus DMET on real catalysts at the 50-qubit scale. Already happening. 2027, the logical qubit era begins. First small fault-tolerant chips. QPE lands on water-class molecules. 2029, catalyst screening pipelines. Hybrid workflows that scan thousands of candidates per week, not per year. 2031, industrial impact. First quantum-derived catalyst in production. Best bet, CO2 reduction or OER. 2035 and beyond, routine. quantum chemistry as a standard step in any new catalyst program. Like CFD became standard in aerospace. Like machine learning became standard in drug discovery. The horizon is short. The molecules are waiting. That was episode 2. Solve the chemistry, save the climate. Catalysts decide whether decarbonization is real. And qubits, they're about to decide the catalysts. If this changed how you think about where quantum matters, hit like. Subscribe. We're posting one episode every day. And tap the bell, because episode 3 drops tomorrow. The HHL algorithm and how it solves the reservoir PDEs that broke us in episode 1. See you then.